We trust our lives to the invisible rules of material physics every day. We drive 2-ton vehicles supported by heavy, coiled metal springs that flex, bounce, and violently compress over every single pothole on the road. But how do the engineers who built these machines mathematically guarantee that those vital structures will bounce back instead of abruptly snapping under the pressure? To find the origin of that engineering confidence, we have to look back to a deadly maritime crisis in 17th century England. Navigators lacked a precise way to tell time at sea, making it mathematically impossible to calculate their ship's longitude. Standard clocks relied on swinging pendulums. On a ship pitching and rolling over ocean waves, a pendulum's swing was constantly disrupted. Sailors urgently needed a mechanical timekeeper entirely immune to physical shaking. Solving this longitude problem required finding a physical material that behaved with perfect mechanical predictability under extreme fluctuating pressure. Without that guarantee, navigating the globe remained a lethal guessing game. Enter Robert Hooke. While the Royal Society celebrated prominent thinkers like Isaac Newton, Hooke was an incredibly prolific doer. He was the experimentalist who built the apparatuses, ran the tests, and solved the practical problems. Hooke realized he could solve the longitude crisis with a completely new kind of clock, a jerk-resistant, compact watch regulated by a tightly coiled balance spring, rather than a swinging pendulum. In testing these metal coils, Hooke uncovered a profound physical rule. He realized that elastic materials respond to the physical stress placed upon them with absolute mathematical consistency. To understand exactly what Hooke discovered, we can look at this force extension graph. The vertical y-axis tracks the exact amount of force applied to an object, and the horizontal x-axis tracks the extension, how far that material stretches as it is pushed to failure. Hooke's clock spring solved the maritime navigation crisis, and in the process, it mapped the invisible mathematical rules governing exactly how every solid object on Earth bends and breaks. Starting at the origin, as we apply force, the material stretches in a perfectly straight diagonal line. This straight line represents Hooke's law, F equals negative kx. The force the spring pushes back with is exactly proportional to the distance stretched. The k in this equation is the spring constant. A high spring constant describes something incredibly stiff, like a heavy trampoline spring, while a low spring constant describes something loose and easily pulled apart, like a plastic slinky. At the microscopic level, this predictability happens because of the material's atoms. Under pressure, the invisible bonds in the crystal lattice stretch tightly apart, but eagerly snap back to equilibrium the moment the force is removed. Physicists call this state elastic deformation. In this linear zone, materials possess a perfect physical memory. They can be flexed, stretched, and reused infinitely without sustaining any structural damage. But right at this distinct marker on the graph, the line stops its upward diagonal trajectory and bends sharply outward to the right. We have reached the limit of proportionality. The mathematical rules of Hooke's law break down completely at this threshold. Past this point, the material stretches wildly with very little extra force applied to it. We have entered the territory of plastic deformation. The material is now yielding to the stress, undergoing an inelastic, permanent physical change. Deep inside the crystal lattice, pressure forces massive atomic dislocations. Entire molecular layers slide laterally past one another, locking into new, unaligned positions. Because the atoms are displaced, the energy from the impact is no longer stored up for a mechanical bounce back. Instead, that energy is lost forever, dissipating into the surrounding environment as heat. By crossing the limit of proportionality, the material's structural history is rewritten. It can never return to its original form. At the far right of our graph, the curve reaches an absolute endpoint, the fracture point. Here, the material violently snaps and completely fails. Every material has a different curve leading to this point. Brittle materials, like glass, hit their fracture point almost immediately after crossing their elastic limit. They shatter with zero warning. Looking at these two comparison lines on the graph, ductile materials, like copper or steel, have a massive survival advantage. They endure a long, drawn-out plastic deformation phase before finally breaking. A material's inherent strength isn't determined solely by the raw force required to break it. The specific shape of its curve on this graph dictates exactly how that material will fail. Modern engineers use this mathematical reality to keep bridges and skyscrapers safely confined within the elastic zone. But they also actively weaponize the plastic zone to save human lives. Automotive crumple zones are the ultimate real-world application of plastic deformation. During a high-speed collision, engineers intentionally force the car's steel frame to permanently deform, crush, and fracture. The breaking metal absorbs the deadly kinetic energy of the crash, converting it into heat and structural damage so that the energy never reaches the human passengers inside. Robert Hooke set out in the 17th century to build a better clock and conquer the oceans. Today, his mathematics allow us to deliberately bend the physical world to our will, safely engineering our survival right up to the breaking point.